Engineering. What did we want to do today is bring you up to speed with Inertia and let you understand what they do and how they do it in their product portfolio. Inertia Engineering is a U.S. manufacturer, and we're dedicated to develop better product solutions for the electrical industry. This is something that we feel very strongly about all the way around. Location is in Stockton, California, which is about an hour south of Sacramento, an hour and a half inland from San Francisco. I said Sacramento and San Francisco. So consequently, it's located in a very agricultural area of the country where almonds are grown and cherries are grown. So it's very much a very beautiful area, along with the vineyards that are around it. Currently, we're in a 150,000 square foot facility. We have another 100,000 square feet that is available for manufacturing, and we're utilizing some of that at this moment. Go back a little bit. I want to tell you about us. We were established in 1995 by Dean Sanders. Dean Sanders was the chief engineer and design engineer and general manager for a company called KPF Switches, which was owned by Kearney at the time. Cooper Industries bought or acquired the Kearney switches and decided to move them to Arkansas. Dean and his staff engineers and production people did not want to relocate to Arkansas, and thus started the company Inertia Engineering, which is involved in what it is today. Very respected in the industry all the way around. It's an ISO 9001 company. It's a certified manufacturer of medium voltage switchgear, automation products, and specialty equipment components for the electrical distribution industry. We have been recognized as one of the industry's leaders in providing quality switchgear, automation products, and we have a customer base that reaches across the domestic U.S., Canada, and internationally. These are some of our blue chip customers from PG&E. We do a lot of projects for PG&E that never get commercialized. Just for the simple fact, they're in our backyard. They're our biggest IOU, our biggest customer. LADWP, Los Angeles Department of Water and Power, the largest muni in the country, and we do business with them. Southern Companies, which is comprised of Mississippi Power, Georgia Power, and Alabama Power. BC Hydro up in Canada, Duke Energy, Hawaii Electric, Luma or PREPA in Puerto Rico, SDG&E, First Energy, AGCO again in Canada, Pacific Core, AEP, American Electric and Power, which has, I believe, 17 operating companies associated with it. And of course, through distribution as well, we continue to do our business through these groups. We have a strong R&D department. We try to look at things from the aspect of what we need to do to improve our product. We don't take any cost out of it due to the fact that that is what we look at when we sell our product to the customer, that we're giving them a very robust type product to work with, so they're not having any problems in the field with it. We set the industrial standards with our products and services throughout the U.S. and North America and internationally. Again, we make robust switches at affordable prices, and we don't compromise on quality. That's kind of like I spoke to just now about the R&D side of it. We are flexible to make various specialty switches for the customer. All they need to do is tell us what they need. We'll do some drawings. We'll pass them back and forth. And once it's signed off on and give us a purchase order, we can move forward. This is something that Inertia has built their business around and for their customers. Let's do some product overview. This is our portfolio. Distribution products from 15 to 35 kV. So they're very cost effective. Again, very robust for harsh environments as well. Transmission switches from 48 kV to 72 kV. Again, the same thing. They're all unitized, All of our switches are unitized, which they go up very easy. They're factory adjusted, so consequently, they're not going to have to adjust them when they get to the field. Sensing hardware, we have a product called Thermal Alert Device, or TAD, which allows you to sense the transformer and to see if it's going to go into a runaway situation. And we can talk a little bit more about that later on in the presentation. A voltage regulator bypass switch, which allows you to bypass the voltage regulator without having to take an outage. This has been around for over 50 years, and it's very much a very safe and easy way to take a regulator offline. Low break devices. We manufacture our low break devices in-house from 15 kV, which is 6, 9, and 1200 amp all the way to 2000 amps. Automation products, which allows you to go have SCADA ready type equipment, and you can operate motor operators from your SCADA control house. This is our portfolio for our distribution and transmission switches. These are our configurations from horizontal. As you look to the left there and down, then you have the horizontal underhung, which we call an avian switch, and we'll talk a little bit about that. Vertical phase over phase. Riser switches, which a riser switch allows you to go from an underground feed to an overhead feed. And vertical tiered outboards, which is again another phase over phase. A delta or triangular type switch as well for a pole top, depending on your configuration of your conductor. Various one-way, two ways, three ways, four ways tap switches as well, and we'll talk about those as well. Again, they're very cost effective. They're extremely robust, built with bus grade copper, and we'll talk more about that as well. And they're factory adjusted and ready to mount, so that's a big plus for the utility and the contractor who's putting them up. We use reverse loop contacts, jaws, and we'll talk more about those. And everything is silver plated, and we'll talk again about that. And the terminal pads are tin plated. Again, we'll talk more about that. And we'll talk about the other aspects of the switch. So Inertia Engineering product line, everything is a side break switch. It's all copper construction, 15, 25, 35, 48, and 72 kV, 6, 900, 1200 amps. We want to go up to 1200 amps, but we don't go above that at all. Our load break devices are 15, 150, 600, 900, 1500, 2000 amps. So we make all those in-house. Everything is unitized construction, again, which allows for quick, easy installation on a pole. Also, it eliminates adjustments, so it really helps to do that. Substation mounting, we can mount into substation. Unfortunately, some substations are a little more difficult to work with, but we still look at the construction of the substation and try to make something that we can mount into it. Control mechanisms for the switches. We use reciprocating, which is an up and down motion, torsional, which is a twisting motion, and a hook stick control, which you would use a hook stick to open and close the switch. Again, there's a regulator bypass switch. It comes at 15 kV up to 35 kV up to 1200 amps, so 6, 9, and 1200 amps. Motorized switch gear, or pardon me, motorized switch operators for distribution and transmission. And I'll show you those in a later slide. And again, we can do those specialized products designated for the client. Again, it's just a matter if they have a special one-off they need, or it needs special phase spacing or some other thing that they need on a switch, we can do that. Basically, we say there's 1.9 million different configurations in the switch world with our switches, so we can try to help that customer develop whatever they need. This is where we play from generation, transmission, all the way to distribution. Basically, our continuous current ratings are 600, 900, 1200 amps. Momentaries, 40 Ka at 600, 51 Ka at 900, 70 Ka at 1200, with a fault close of 30 Ka. Here's that avian switch, that underhung avian switch I spoke about earlier. So this was developed to keep birds from going face to ground if they were in a situation where they would land on the switch and create an outage. So consequently, the hot parts are down underneath, and the bird really can't get onto the switch and go face to ground. These are all SCADA ready switches. If we put a motor operator on them, they give you clear view if the switch is open and closed because you can see right up to it. Again, it's fully unitized. It goes right up. I can use a steel cross arm, a fiberglass cross arm on these as well. These are tested to what we call the California fire exemption requirement. So basically what that means is the requirement is, or the test is, you have very highly combustible material you put down on the ground, and you put the pole into that material and put the switch on the pole. And you put fans onto that material to blow on it in case there's sparks that fly down and it could create a fire. So you open and you energize the switch and you open and close it, I believe it's 10 times. So if there's any arcing or sparking coming off that switch, they would fall down into the material and create a fire. Again, we passed this with our switches, and it's a published document that the California fire exemption, I believe it's called CDF, publishes every year. So we have let me go back up. The horizontal configuration. Again, this is kind of the common one you see out in the field all the time. You can dead end on the switch if you like. We recommend you don't dead end, but you have the capability of dead ending on this. If you look at the operating mechanism to the lower left, that's a hook stick operator, and we'll talk about that as we go around. The configuration on the lower right-hand side is a set of reclosers with a switch above them, so they could de-energize the reclosers with this switch if they need to. Here's that vertical riser configuration. Again, if you look at the photo, you've got a feed going to the underground, and it's coming down from the overhead to feed the underground and vice versa. So consequently, that's what a riser pole is. It's a 180-degree turn on the pole. So consequently, you have a very easy way to train your conductor up and down. Delta configuration of pole mount. It's on top of a pole. Depends on what you way they have their conductor run. This one has a static wire on top of it. I'm going to blow this up and show you that's a motor operator on that pole. That's sitting 10 feet off the ground. It's for a snowpack that goes up in here. This is in the Sierra Nevada. So consequently, snow gets up to it. It keeps it from being 10 foot off the ground, keeps it from being covered up in the snow base at that point. Phase over phase. If you look at this configuration, on the left-hand side, again, you have a hook stick operator. You have, it looks like a pole going down. That's a down rod for a mechanical or a manual operating to open and close the switch. You could also have a motor operator on that. These switches, the blade drops down from the bottom and back up to open and close. This is called a tiered outboard. Again, it's a phase over phase. If you notice, the switches are sitting upright, so they would open in a horizontal position, the blades. Especially kind of switches, this is an alley switch. So consequently, the pole is on the right-hand side there, as you see, and the conductor is being trained down off the side of it. So consequently, we can do those kind of switches. This is very unique one. This is a 72 kV that came in with a unitized backbone on it. This switch went up in 3 hours and was completely ready to go in 3 hours, which would normally take about 3 days to do. The downside is it has to come in on a flatbed truck because only one switch could come in on a truck at a time. You need a crane to lift it up, but installation is very quick and easy. There's a cost factor, obviously, with the putting it on the pole, but it is a savings all the way around to the utility. Various switches, tap switches, 1, 2, and 3-way. Now, what is a tap switch? A tap switch allows you to take and change directions with your conductor. Let me just blow this up. If you can see, the conductor is running, say, one way, and you can tap off and go the other way. So consequently, On this particular one, it's a three-way tap. This one is over here is a two-way tap, so it's the direction is totally different. And we can see here again, just totally different. It changes direction all the way around. Again, these are different pole type taps. This is the three pole different type configuration. If you look here, it comes down, it turns to the right. If you see it, it's tapping that, it keeps it continue on. And if you go down further, it turns to the left. So consequently, a little bit different. Again, a tiered outboard tap on the left, a pole top center mount, and a pole type riser type. Here's a switchgear construction. This is what I was talking about earlier. This is a phase unit, a single phase unit. And if we look here, we can see, my arrow will not show you this. There's an interrupter on top of it that is on the very top. That's called a expulsion interrupter. And we'll talk a little bit about that as well. The blade is in the jaws, reverse loop contact jaws. We'll talk about that as well. At the bottom of this insulator on the left, there's a double seal stainless steel ball bearing. That's a cross arm. So we're just seeing one phase unit right here. So basically, this is our construction. We can use a one-piece heavy gauge galvanized steel cross arm, or we can use a fiberglass cross arm. We use a one-piece interface connection rod for the switches to open and close with. That can be fiberglass or it can be steel. We use a bell crank, which operates the interface rods that opens and closes the switch itself. We use reverse loop contact jaws, and we'll show you those in the next slide. And also we'll show you the blade and talk about that. To hang the switch to the pole, we use a 1/4-inch galvanized steel and with slotted holes. So consequently, they can hang it, and I believe they're 12 inches apart. Amp rupter, again, the low brake device. Inside of that, that's called a expulsion interrupter. Inside of that interrupter, and we'll talk on the next slide, is a white probe that quenches and helps break the load inside once you do a low brake opening. We use a heavy duty 3/8 conductor, so you can, or 3/8 angle, so you can put the conductor dead in straight into the switch. That's kind of critical in a sense because our competitors use a 1/4 inch on that. So there's from that phase unit a while ago we looked at, up top here is that interrupter. So inside that interrupter, again, is a white probe. It comes out of a low brake elbow. If you ever looked inside or saw a low brake elbow, it's the same white probe is inside of that. So when it makes and breaks the full low brake, it's got orange quenching material. It's going to be excited gases when I break that circuit. And in the back here, you see some vents, and you'll have a little smoke come out of those vents. That's common. That's common because it's extinguishing those high energy gases at that point. So it's just extinguishing gas. Sometimes you'll hear this called this interrupter called a puffer, just because of the smoke that comes out of it. So if you look at the jaw, which is where the blade is inserted to, that's a reverse loop contact jaw. If you look the way it's designed, it curls around, comes around. So consequently there, when it's energized, it starts putting pressure onto the blade. If I had a surge in the power, it just clamps down tighter on the blade, so it does not try to expel the blade out of the jaw. So that's a safety feature, if you want to call it that. It was designed by Westinghouse engineers back in the 1950s, when Westinghouse was the leader in the utility world. And it allowed switches to go up to higher voltages, 115, 230, and above. So it allowed all that to happen. So it was a patented item for many years. We put this on all of our switches, whether it be 15, 25, 38, 46, or 48, and 72 kV switches. All of our construction is the same. So we put it on all of them. The jaw itself, if you look at the color of it, is silver plated. The blade, which goes in the jaw, is silver plated. It helps cuts down on resistance as well as corrosion. We use a shunt, or it could be called an arcing horn, and we use a trip arm off the blade and a catch arm on the interrupter. There's a 2-inch gap right there. When I come out of the jaw with the blade, it transfers the load, the energy load, onto the shunt, and then transfers the trip arm to the catch arm before making the interruption. So I never have an arc in between. It's very important all the way around. These are air brake switches, but you don't want to have an arc burning. Construction of the switches, we use a bus grade copper C110. Actually, it's 99% conductive and not subject to unseen porosity. Porosity is when they pour the copper or even aluminum, or it's would have little air holes or bubbles where it comes up. So porosity is very minute in this. Again, we'll take the terminal pads at the end of them, they're copper as well, and we template them. So why do we template them? If I have two dissimilar metals, copper and aluminum, the copper salts will start eroding the aluminum. It's just a common thing. It happens. So we template them to put a neutral position in between them, and it works admirably well. So anytime we template them, that's what happens. So it has a neutral position between it, and you can put aluminum lug right there onto that copper terminal pad with templating. So that's why you do that. Again, on the left, that's a 6 and 900 amp contact set with the blade going into the jaw. Again, we silver plate all of that. On the right is a 12 and 1600 amp contact set, which would be a dual blade. Each one of those blades is rated at 600 amps. So on the rotating insulator, we have a double seal stainless steel ball bearing setup. This withstands hazardous conditions and environments. We soft fog tested this, and we also tested it on the coast in Hawaii and Puerto Rico for over 15 years before we decided to put it on our switches. It allows the blade to glide very easily. This eliminates a lot of open and closing issues, and it works admirably well. We've been doing this now, probably the last 7 years. So it was a period of time before we decided to do this. And again, well, it separates us from other people as well. Again, station post insulators, primarily we've always used MacLean as well. Interrupting devices, we talked a little bit about those in earlier here, but we make all our interrupting devices in-house, from our arcing horns, our arc whips, high-speed whips, expulsion tubes, which is vacuum interrupters, which is a V4 and VI7, and our sectionalizer switch, all in-house. So an arc whip is good for a 1/2 amp per mile, up to 20 miles for 10 amps. With a high speed, you could go up to 20 amps, which will allow you probably 40 miles. Primarily, an arc whip is good for line charge. So when you de-energize a conductor, it still has energy inside of it, and that's called line charge. So consequently, you want to eliminate that line charge. So you can use a whip to do that with it. As far as interruption, we use an interruption device. This again is an expulsion interrupter. This is good for 600 and 900 amps. Again, the gas extinguishes out of these vents in the back. Inside of here is that white probe. When I make and break with this mechanical side, when it comes out and I activate that control arm, it pulls the probe apart, de-energizes the circuit. On a low break situation, it's good for 600 to 900 amps. So if we want to go to a higher ampacity, and we like to do this at 38 kV and above, on this particular one, this is a good one for 38 kV. This is called a V4. It's a vacuum bottle in here instead of a probe inside of it. In vacuum, there's no arcing and sparking. so there won't be any smoke coming out. And there's no way for the smoke comes out because it's all enclosed in a vacuum bottle. So what you see is a vacuum bottle on the backside, the round part, and the front part is the mechanical operating that operates the bottle. This is very unique. So we worked with Eaton, who we get our vacuum bottles from, for 5 years to try to develop a single bottle, 2000 amp bottle. In the past, we used to use the one on the left with a white case on it. It's called a 3-bottle setup inside of it. There are 3 individual bottles in there. Downside of it, you had to time them all together when you open up or made a low break so that they all opened up at the same time. Or if one opened up late, you could have an event. An event would mean that you could have an explosion of this thing. And the other side of it was the ratings on them are lower all the way around. The weight, 62 pounds on the cantilever action on the end of your switch versus 17 pounds. Very superior bottle all the way around, very superior interrupter. We now put these on all of our 72 kV switches. The ratings are superior on this. This is a 2000 amp bottle. Now our switch is only rated to 1200, but this is a 2000 amp bottle. Cable charge, 70 amps. On that 3-bottle setup, the best I could do would be 10 amps. So very, very much higher rated all the way around. And again, we use these on all of our 72 kV and also vacuum on our 46 or 48 kV switches. Control operation options. Again, this is the way you open and close the switch. Torsional is a twisting motion. If you look to the right there, you see the gentleman is twisting it to open and close the switch. I have high torque value down low where he's at. As I go up the pole, I lose that torque value, and it's called pipe wrap. And as I get higher on the pole to where the switches are, I may have to stage the blades to go into the jaw because they will not enter at the same time with that twisting motion. And that's an adjustment that would have to be made. It's also wood poles now are not cured like they used to be. So as they sit in the field, they'll start twisting. And if I have a torsional, it starts twisting that pole and it puts it in a bind, and I can't operate my switch. So that's a little more of a situation where torsional is not a good value, although historically it's been in the field forever on switch controls. We can do torsional on all switches except for our phase over phase. So if a customer wanted torsional, we can do it. We recommend, though, the reciprocating, which is called a pump pedal, which is up and down motion. The up and down motion allows the switch to open and close very, very good. It also, as I talked about, as the wood starts curing and twisting, that twisting motion, I can, it doesn't affect my operation of that switch. I can still operate it without any problems. So there's no adjustment required at that point. Again, here's another control mechanism, the hook stick. So basically all I do is take a hook stick in the air, operate the switch, and it's open and closed. Again, it's very much a plug and play type situation where I just put the switch on the pole. Don't put a down rod anymore for the control handle, and I'm done. Motor operators, this is automation. So why would we use automation? This has actually happened. This was in California in the Delta Islands, where they had to go up to a boat, go up and do some switching on it. The guy had to put his hooks on and climb the pole to make it happen. This is a standard motor operator and what it looks like. So if I open the cabinetry, let me go back, open the cabinetry, and I blow this up, I can show you exactly what it looks like. Up at that bar, that black bar up in the right, that's a sensor for the door sensor. So when I open the door, it goes back to the control house and says somebody has entered this cabinet. There's a rain gutter on top, so if there's rain or moisture, it's not going to fall down on you. I have a lamp tester. I can test the lamps on all the lamps in it. If a power supply, low battery lockout. So what that low battery lockout means, if I do not have enough voltage in the battery and it's set, it will lock out the motor operator and not allow you to operate the switch. So if you don't get halfway out, they would not then run out of voltage, out of power on your battery, you wouldn't create an arc. So it will lock it out. So it's got a low battery reset as well and a battery test. So we run a battery test all the time on these to make sure. Interconnect pin removal. If you look down to see that yellow tag, that's the interconnect pin. We'll talk about that in a minute. The decoupler, the black handle to the left, that's pushed in. That's where we decouple the switch. So we'll talk about that. The remote and local, when I put it in remote, switch in remote, that's for SCADA, and the control house has control of the switch. If I put a local, I have locally, when I'm standing in front of this, I can operate, open and close the switch right there. I put a 120 volt plug, so I plug test equipment into it as well. I put brush guards over the close and open buttons so I don't accidentally hit them. And when I open it up, so I have to lift them up. The decoupler, that's how I decouple the switch, down to the left here. I pull it up and I decouple the switch. The pin, interconnect pin, I pull it out, I de-energize the motor operator. There's a manual handle, I can operate it manually in the back as well. So that's kind of the internal of a motor operator. There is a wind latch on the left at the bottom to keep the door from hitting you if you were out in the field trying to work on this, keep the door from hitting you all the way around. They're all SCADA ready. This depends on your communications modem. If you put cellular in it, radio, or fiber, just depends on what you want, what your communications modem is. So all of the motor operator are ready to go on SCADA. This is again is a motor operator with a Schweitzer relay in it. So we'll talk with the next slide about the Schweitzer relay. So this allows me to put a Schweitzer relay in. If you see that point right there, the other old one versus this one, I'm going to try to blow this up too. It's basically the same. I have an open and close on this Schweitzer on this 2411 relay. I have a lamp test as well. The same application, remote and local. And I have the lights as well. This one is designed for a smart switch, and we'll talk about that in a minute. Right there's where I decouple, and there's again so that interconnect pin. So let's go to the next slide. So if you look at the switch on the right, it's got current sensors on it. I can put current and voltage sensors on it. What happens if I lose current or voltage? It senses it and it can go back to that Schweitzer relay. It can become an automatic sectionalizer and open and close that switch without having to have somebody at the switch to open and close it. In other words, if I lost, say, current, it could have a time delay and open up that circuit. And when the voltage comes back on, it senses it. It could be a time delay and closes in when it needs to. Or it could be operated by the control house. MPS, non-interrupting bypass switches. This is the one for voltage regulators. A voltage regulator on that pole is a very dangerous piece of equipment. So what a voltage regulator does, it's if there's a dip in the power, it starts ratcheting up to try to get more energy through the line. If there's too much energy in the line, it ratchets us down to try to eliminate that energy in the line. If you cannot get it in neutral, there's a neutral position in it. If you cannot get it in neutral, to take it offline, and being offline, if there's a reason to take it offline, if it's all of a sudden becoming damaged and needs to be repaired, the utility is trained to take an outage to take it offline because it is a dangerous piece of equipment. Now, the non-interrupting bypass switch was developed over 50 years ago to safely take it offline without having to take an outage and reliability. So how does that work? I use a hook stick, either bypassed or cut in. Bypass meaning I'm bypassing the voltage regulator. And all I do is pull down on it. So what happens is I pull down on it. If you look to the far right, try to visualize that you see those jaws, you see those reverse loop contact jaws. It's a blade that goes right there. It's coming down. It would slap across and it picks up on a copper trolley and transfers all that high energy that's in the voltage regulator through those that loop through to the voltage or to these high voltage resistors and dissipates that energy and controls it. Now, if you have to visualize going down, that voltage regulator is sitting below it, I can open up my disconnects and I have isolated it totally. If I next picture, that's basically what's happening up here on in the far right. This is Power Tech in Canada where we were testing this. The voltage regulator is sitting below. He's getting ready to bypass it. And once he bypasses, he can open up the disconnects. And he's totally isolated, and they can take and remove it all the way around, or replace it, or repair it, whatever. That opening and closing with the hook stick happens in 3 to 5 cycles, so it's very quick and fast. So when I open and close, it's and there's no stopping. Once it goes, it goes. It's not going to stop in mid stream, but it's going to go and it's going to open and close that way very quickly. TADs, thermal alert device. We talked about those earlier. So what a TAD is I put a sensor on the side of a transformer, primarily in-ground transformers or in vaults. And the sensor is put on with a hook stick and it's magnetic and it goes right to the side of the case. So that gives us information on the temperature rise of the transformer. Goes back to the monitor and gives us data back to a cloud-based collector. And if we see from the parameters we set on the transformer, we can tell, okay, is it rising above those when I have a high usage? Is it going to go out of control? And we can determine that from that data exactly what's going on. And the alerts can come back by text, by emails, by phone calls. So it's a matter of coming back. It is a watertight enclosure all the way around. A question is, okay, a magnet will not stick to stainless steel if we have a stainless steel enclosure. We have a way to apply it to stainless steel through an adhesive, the sensor. So consequently, this is something that's a brand new product for us. We have over 10,000 of them deployed right now, and we're looking to deploy some more. Here is something as well. This is a new switch. It's called a vacuum brake switch, or group operated vacuum brake. So basically, we talked when we talked about the motor operator with the Schweitzer unit. These are voltage and current sensors on the end of the switch, on both sides of the switch. It kind of looks like long tubes. So they're sensing voltage and current. This switch is, let me go to the next slide. And there we go, current and voltage. These would be single phase units. How does this work? There's no arcing and sparking in this particular switch. So all the switches we manufacture are side brake or air brake switches. Now this is a vacuum switch. So consequently, it's got a vacuum waddle internally. This is for fire mitigation application. It could be that you could put it up for existing switches. It's not in a fire mitigation type area as well. It can be operated by a hook stick operator. It can be operated by a motor operator, or it can be a manual handle. It's down rod to it. So it's got various ways to make it happen. There's no arcing or sparking in vacuum. So you're not going to see any type of arcing. There was a study done by a utility in the West that had high-speed cameras on a air brake switch, and they saw that there's a possibility that some arcing could come out of a switch, and so to concern again is could that arc fall to the ground and be in some dry grass or something and create a fire? So consequently, this is what we're calling a fire mitigation switch all the way around, but again, it can be utilized as a standard switch too. Phase units or a phase unit for a disconnect. So we built these recently and they're in our portfolio for 15 and 25 kV, 6 to 900 amps. You can utilize these over a set of reclosers. This would be a set, would be going a three-phase set with the reclosers and take reclosers offline with them. Again, momentary is 40 amp, 40,000 Ka, 10 cycles, 25,000 Ka, 3 cycles, all the way around. Again, it's something that's available to you at this point. Our standards, we build to IEC standards, ANSI, C37.30 standard, IEEE 1247. We also soft fog test the ASTM B117. We've soft fog tested at ETRAC in the Georgia Tech area. We primarily use 2 different third-party testing facilities, PowerTech in Canada and KEMA in Pennsylvania for our test reports. But these are our standards all the way around. So consequently, that is what Inertia, their portfolio is at this point. If you have any questions or concerns, feel free to reach out and contact us. Both myself and Caitlin Terry could answer any of your questions, and our engineering staff as well. Thank you for your time, and we'll be looking forward to meeting and talking to each one of you in the near future.